Welcome to this problem solving session number 7. In this problem solving session, we are going to solve problems related to quantum master equation, Transmon qubit and Fabry-Pérot cavity. As the first problem, let us begin with this one. You are asked to derive the dissipative block equations using quantum master equation. We have already learned about quantum master equation in the lecture classes. The evolution, this equation, quantum master equation, basically gives the time evolution of the density operator or the density matrix. So this is equal to 1 by I h cross h is the Hamiltonian, h rho. This part gives the coherent evolution of the density matrix. And then we have terms pertaining to the dissipative processes. For suppose the z process is happening at the rate gamma j, there are all kinds of processes, and then we have this Lindblad operator, and aj is the operator that connects the system and the environment. So this is the Lindblad operator, and this Lindbladian operator is given as this part is equal to a rho a dagger minus half a dagger a rho minus half rho a dagger a. So using this master equation, now let us derive the block equation in the presence of various dissipative processes. So we have a two-level system with energy states denoted as say kg, that's the ground state, and kt is the excited state. And there are primarily three processes that occur. First of all, transition from the upper state to the lower state, say excited state to ground state, it happens at the rate gamma minus. So this process refers to emissions. And there are process, so first process, we are having transition from the excited state to the ground state, and we have also process where transition can occur from the ground state to the excited state, and that rate of occurrence is say gamma plus. So this is also a process we have. And finally, we, in addition to all these things, we have this pure dephasing, and that occurs at the rate, so pure dephasing also occurs, and that happens at the rate say gamma phi. So we are going to consider these three processes, and we can define relaxation operator corresponding to these three processes. For the emission process, we have the operator, let us say this is the relaxation operator, a minus is equal to, we are going from the excited state to the ground state, and this is, as you can see, this is the atomic lowering operator sigma minus, and this process is happening at the rate gamma minus. And then we have this absorption process a plus, where we are going from the ground state to the excited state, and this is the atomic raising operator, and this process is happening at the rate gamma plus. And finally, we are having the relaxation, this pure dephasing processes, and here the relaxation operator is, we are going from the excited state to the excited state, and there is a prefactor of square root 2, and it is happening at the rate gamma phi. Now incorporating all these things, we can write down the quantum master equation. So the master equation would be rho dot is equal to 1 by I h cross h rho. I will soon tell you what is h, the Hamiltonian. And let me now put up all the processes here. For gamma minus, I can write sigma minus rho sigma plus minus half sigma plus sigma minus rho. All these are operators, and we have here minus half rho sigma plus sigma minus. And for the process related to this absorption gamma plus, that would be sigma plus rho sigma minus minus half sigma minus sigma plus rho minus half rho sigma minus sigma plus. And finally I also have we have 2 gamma phi, and that is due to the pure dephasing. Let me write it explicitly. We have here terms like this, okay, minus half e rho, and then I have minus half rho e. This would become actually simplified because we know that this part is actually scalar product. This is equal to 1 and this is equal to 1. Anyway, we'll do that. So this is the quantum master equation, where this Hamiltonian is, I write the diagonalized form here, h cross omega atom by 2 sigma z is the Hamiltonian. That means that my excited state has energy h cross omega atom by 2, and the ground state I am taking the energy as minus h cross omega atom by 2. So therefore the energy difference is simply h cross omega atom between the two energy levels. So this is what we have. Okay, so now let us work out various terms. For example, how this element of the density matrix evolves in time. So rho e, which is equal to e rho dot e, and we can work it out. In fact, let me do the calculations term by term. So first term we have here is e. Let me first calculate h rho e, and if I open it up, it would be e h rho minus rho h e, okay, or h rho e minus e rho, it is rho e. So okay, you know that h of e is equal to the Hamiltonian is h cross omega atom by 2 sigma z e. Now if I know sigma z operator is 1 0 0 minus 1, and if I take the this vector ket as this column matrix 1 0, okay, so I am taking kt as 1 0 and kz as 0 1, then I will have, if I do the math, you will get it as h cross omega atom by 2 1 0. So this is basically h cross omega atom by 2 ket e. Similarly, we will require it later when it operates on the ground state. You will get h cross minus h cross omega atom by 2 kz, and therefore we have e h rho e is equal to, by the way, just note that because h e is equal to h cross omega atom by 2 ket e, so if the Hamiltonian, because this is a Hermitian Hamiltonian, if it operates on the bra of that, so your bra e, you are going to get again h cross omega atom by 2 bra e, and therefore from here I can write this as h cross omega atom by 2 E rho E, and the other one E rho h E is also equal to h cross omega atom by 2 E rho E. And as you can see, because both these terms are equal, so what I will have here is this, that E, this operator commutator h rho E is going to give me simply 0. Okay, now let us go to the other terms. Now let us calculate this particular term, E gamma minus sigma minus rho sigma plus minus half sigma plus sigma minus rho minus half rho sigma plus sigma minus E. So to do this, let me first work out this term. So that is E gamma, okay, just let me, gamma minus is anyway is a constant parameter, so let me work it out. Sigma minus rho sigma plus E. Now this is easy to see because sigma plus is the atomic raising operator, and if you are operating on the excited state, you can explicitly do the calculation also. You will immediately get it to be 0. Okay, and to show it to you, sigma plus, you are basically going from the ground state to the excited state. So sigma plus is, you are going from the ground state to the excited state, then you are operating on this kT, and because this is orthogonal, so this is going to give you 0, right? So this term is going to give you 0. Then we have to work out, once this is done, what we are left, we have to work out E, say sigma plus sigma minus rho, right, rho E, this term. So this, if I just put it, the whole thing explicitly, then you will get E sigma plus is, you are going from the ground state to the excited state, right, and sigma minus is, you are going from the excited state to the ground state, and then here you have rho E. So this is, as you can see, this is a scalar product, it is equal to 1, this is normalized, this is also 1, so you will be left out with simply E rho E. Again, similarly, you can show that E rho sigma plus sigma minus E, that would be equal to, if I do it explicitly, you will have rho, and here you will have E, this Z here, Z E E, so this is also equal to E rho E. So therefore we have calculated all these terms, so I can therefore work out this particular term. So this would be, if I put all the terms there, I will have it as gamma minus half E rho E minus half E rho E. Okay, and therefore I will get it as minus gamma minus E rho E. I can write it as rho E. Okay, so this is what I have. Similarly, I can work out this term with the absorption process, the term involving the absorption process, that is gamma plus sigma plus rho sigma minus half sigma minus sigma plus rho minus half rho sigma minus sigma plus you will have E here, and if you work it out, please do that, you will immediately get it as gamma plus rho ZZ. So finally we are left out the pure term with the pure dephasing, and that is E 2 gamma phi. We have E rho E. Just let me remind you, here I have do this simplification. As you can see that this is equal, this is 1, and similarly this is 1, so therefore I can write it very simply as the first term is fine. Then we have minus a half E rho minus half rho cap E, and the whole thing is, I have to put E. So if you do it, you can immediately see that you are going to get twice gamma phi, and here you will have, first term will give you rho E, then the second term you will have half rho E, and the third one is going to give you half rho E. So therefore you have 2 gamma phi rho E minus rho E, so contribution from this term would be 0. Therefore what we have is rho E. Actually you will have time evolution of this matrix element in the would be in the density matrix for rho would be E rho E is equal to minus gamma minus rho E plus gamma plus rho ZZ. Now because we know that rho E plus rho ZZ is equal to 1, so without doing any further calculation I can simply write the time evolution of this rho ZZ would be equal to, I should put rho E here, okay, time evolution of this. Maybe earlier also I have to make the same correction here, I just left one, okay, this you have to put. So time evolution of this particular element rho ZZ would be equal to, because of this relation we will have simply it as gamma minus rho E minus gamma plus rho ZZ. Okay, so these are the two relations we get. Now let us calculate rho ZE, time evolution of the density matrix element rho ZE. That would be is equal to Z rho dot E. Again let us do it term by term. First of all let me work out Z H rho E. So this would be equal to Z H rho E minus Z rho H E, and because already we have written down this, let me remind you again that He is equal to H cross omega atom by 2 E, and H when operates on the ground state you will get minus H cross omega atom by 2 Z. Because of this eigenvalue equations I will get here the terms as, here I will get it minus H cross omega atom by 2 Z rho E, and from this term I will get it as minus H cross omega atom by 2 Z rho E. Okay, and combining these two, I will get minus h cross omega atom rho ze. Now let us work out this term, z gamma minus sigma minus rho sigma plus minus half sigma plus sigma minus rho minus half rho sigma plus sigma minus. Okay, let us do it term by term again. So first of all, this one z sigma minus rho sigma plus e, this actually, as you can see, would be equal to 0, because sigma plus, when it is operating, this part if you see, when it operating on the excited state, there is no more excited state to raise it, so therefore this is going to give me us 0. Then let us look at this term now. So we have z, this particular term, sigma plus sigma minus rho e. Okay, here again, when sigma plus operates on the ground state, effectively it's going to give me 0. Okay, because it is operating on the bra, so this is going to give me 0. Okay, let me do it explicitly. You will have z here, and sigma plus is you are going from the ground state to the excited state. Okay, and here sigma minus is you are going from the excited state to the ground state, and you'll have rho e here, and because these are orthogonal, so this is going to give me 0, so therefore this will be simply 0. Now let us look at this term, that is z rho sigma plus sigma minus e. Now when sigma minus the atomic lowering operator, it will lower the excited state to the ground state, so we will have z rho sigma plus z here. Okay, and then sigma plus, it's going to raise it, so therefore we will have z rho e. You can actually do the explicit calculation also, so therefore I can finally write the whole thing as z gamma minus sigma minus rho sigma plus minus half sigma plus sigma minus rho minus half rho sigma plus sigma minus e, that is equal to this is, I can write it as rho ze, and you will have it as, I think, another term in the similar way. Yeah, you will have only this, so because of this half term, you will have minus gamma minus by 2 rho ze. Okay, so this is what you will get. Again, proceeding exactly the same way, we will get z for this gamma plus, the term associated with gamma plus, that would be sigma plus rho sigma minus minus half sigma minus sigma plus rho minus half rho sigma minus sigma plus e. This, if you work it out, you will find that this would be minus gamma plus by 2 rho ze. All right, then finally we are left out with this pure dephasing term, that would be, let us work it out, that would be z here 2 gamma phi, I have here e rho e, then I have minus half kt by rho minus half rho e, then I have here e. So this is very simple. As you can see, you will have 2 gamma phi, and rest of the terms from there you will get simply minus half. So here you will have it also, I think, yeah, you will have rho ze. So you have minus gamma phi rho ze. Now you can combine all the terms and we'll get the time evolution of this density matrix element rho ze is equal to, which is 0 dot e, and combining everything you will get it as I omega atom rho ze minus, you will have gamma minus plus gamma plus by 2, and you will have plus gamma phi rho ze. Alright, now we are left out to find out what is the time evolution of this density matrix element, and that is easy because we know that rho ze is equal to rho dagger ez. So utilizing this we can immediately write time evolution of the density matrix element rho ez is equal to minus I omega atom rho ez minus gamma minus plus gamma plus by 2 plus gamma phi rho ez. So we have obtained all the evolution terms for the density matrix element. Now let us work out this particular problem. The entangled state of a 2 transmon qubit is given as, the wave function is, or the state vector is given to you. You are asked to find out the reduced density matrix corresponding to either of the transmon qubit. So there are 2 transmon qubit and their combined state is given as psi is equal to 0 0 plus 1 1 by root 2. In fact, you know that the first 0 here correspond to the first qubit and second 0 correspond to the second qubit, and here 1, this first one correspond to the first qubit and 1 here correspond to the second qubit. Now this you cannot write it as a product of 2 states. Say state of the first qubit is say phi 1 and the state of the second qubit as phi 2. We cannot write it, we cannot separate it into 2 such product states. This is not possible, and that's the reason this particular state is an entangled state. Now to solve this problem, let me first find out the density operator. So rho would be equal to ket psi bra psi. Take the outer product, then I will have here, let me write the terms explicitly. I have here, because of 1 by root 2, 1 by root 2, I'll have half here, and here I have 0 0 plus 1 1, and then bra 0 0 plus bra 1 1. Okay, this is I have. If I now open it up, then I will have half ket 0 bra 0. You see this first qubit, I will take the direct product with this qubit, first qubit of this term here in the bra. Similarly, this one I will have with this one, and similarly this one I will have with this one, this I will have with this, and similarly other term. In total I will get 4 terms. So let me write all the terms here. This would be I will have 0 0 plus 0 1, direct product 0 1, and you will have 1 0 direct product 1 0 plus 1 1 direct product 1 1. Alright, so this is what we'll get. This is for the first qubit and this for the second qubit. And now to find out the reduced density matrix for the first qubit or first transmon qubit, let me write, I will have to take the I will have to trace out second transmon qubit. So I will take trace over the second qubit, transmon qubit, and as you know, when we'll take the trace operation, we have to operate it on the, I'm now taking the trace operation on the second qubit here, and if I take that operation, you know, this outer product will simply become the scalar product, and I will have it like this here 0 0, and you will have 0 0 plus 0 1, I'll have 0 1, this is all. I will also have 1 0, I'll have 1 0 here, and I'll have 1 1 here. Now K0 and K1 are orthogonal to each other, and because of that, this is going to give me 1, this is going to give me 1, but these are orthogonal, so this term will vanish, and therefore I will have rho 1 reduced density matrix for the first transmon qubit would be a half 0 0 plus 1 1. In fact, I can write it in a matrix form as well, and that would be half 1 0 0 1. Okay, exactly in the similar way I can calculate reduced density matrix for the second transmon and transmon qubit, and for that I have to trace out first transmon qubit, and if I do it again in the similar way, the operation scalar operation would be on the first qubit. So here I will get 0 0, and here I will have the second transmon qubit part will remain as it is, and here I will have 0 1 0 1 plus 1 0 1 0 and 1 1 1 1. Okay, and clearly you will get this term would be half 0 0 plus 1 1, and this is the same as rho 1. This would be half. In matrix form we can write it as 1 0 0 1. Now let us work out this problem on Fabry-Perot cavity. I believe doing this problem will teach you quite a bit about cavity. The problem goes like this. You are asked to consider a planar cavity of length 1 centimeter. The cavity is resonant with light of wavelength 1 micrometer. The photon lifetime inside the cavity is measured to be tau p is equal to 1 by gamma p, where gamma p by 2 pi is equal to 1 megahertz. The problem has 5 parts, and we will do it part by one by one. In the first part of the problem, you are asked to find the free spectral range of the cavity. So let us do it first. So you have already learned about free spectral range. What is it in lecture 22? We know that the free spectral range is given by this formula, that is c divided by twice into the length of the cavity, and c is the speed of light in free space, and that is 3 into 10 to the power 8 meter per second, and d is 1 centimeter, which is 10 to the power minus 2. So therefore it is easy to see that you will get 1.5 into 10 to the power 10 hertz, which I can write as 15 into 10 to the power 9 hertz, and we know that 10 to the power 9 hertz is 1 gigahertz, so therefore I can write it as 15 gigahertz. So this is the free spectral range. Okay, now let me go to the second part. In B, you are asked to compute the ratio of Q by F, that is the quality factor by finesse. This ratio you have to calculate for this cavity at the wavelength lambda is equal to 1 micrometer. We know from our class that this ratio of quality factor and the finesse of the cavity is an integer, say m, and this integer gives the order of the cavity resonance, and we know that this order of the cavity, that is m, is equal to the number of wavelengths in the length of 2D. So we know this relation that m into lambda is equal to 2D. So from here we can easily find out m is equal to 2D divided by lambda. Therefore, this ratio of quality factor and the finesse is equal to 2D. D is 1 centimeter, that is 10 to the power minus 2 meter, and lambda is 1 micrometer, so therefore it is 10 to the power minus 6 meter. So if you do it, you will see that this ratio would be 2 into 10 to the power 4. Okay, let us go to the third part. Now you are asked to find out the finesse of the cavity. So we also know the formula for the finesse. You please refer to the class lecture class. You will see that I have written down this particular formula. Finesse is equal to 2 pi into the cavity lifetime, photon lifetime there, into the free spectral range. Okay, now this cavity photon lifetime is tau p is equal to 1 by gamma p, and we already calculated free spectral range, and gamma p is given to us as 2 pi into 1 megahertz, 2 pi into 1 megahertz. So if I put the parameters in the formula, I will get 2 pi into gamma p is 2 pi into 1 megahertz, which is 10 to the power 6 hertz, and free spectral range we have already calculated, that is 15 gigahertz, so 15 into 10 to the power 9. So you will see we'll get it as 15 into 10 to the power 3, or simply 15,000. That is the finesse. Now let us go to the fourth part. In part D, you are asked to find the wave numbers at which the intra-cavity intensity is half the maximum value. The intra-cavity field intensity is related to the maximum intensity by this expression. So I is equal to I max divided by 1 plus 2 into finesse divided by pi whole square sine square k into d. D is the length of the cavity, k is the wave number, f is the finesse. Now for I is equal to I max by 2, we can see that we'll have 2f by pi whole square sine square kd. K can take two values, so it may be, so let me just put it appropriately here. Let me write k plus minus d is equal to 1, and from here I have sine k plus minus d is equal to plus minus pi divided by twice into the finesse. Okay, so we have k plus minus is equal to plus minus 1 by d sine inverse pi divided by twice that of the finesse. Now we are given d is equal to 1 centimeter or 10 to the power minus 2 meter, and finesse we have calculated as 15,000 or 15 into 10 to the power 3. So if I put all these things there in this formula, then you will see, you please do that, and you will see that you will get k plus minus is equal to plus minus 0.0105 per meter, or I can write it as plus minus 1.05 into 10 to the power minus 2 per meter. So this is the required wave number. Now let us do the final part of the problem. Suppose that you change the wavelength by delta lambda before you find the next cavity resonance. What is delta lambda? Okay, let us do it. You know, if the wavelength increases, let me write here, if the wavelength increases, the next resonance that you are going to get, the next resonance is the one when we'll have one fewer wavelength fits into cavity, right? So what does it mean? This implies that the resonance condition, we know that this is twice into the length of the cavity is m into integral multiple of the wavelength, and this would be when you go to the next one, you will have lambda m minus 1, and here you will have m minus 1. So we can use this relation to work out the solution of this particular part, because delta lambda here is difference between the wavelengths of the nearby resonances. This is lambda m minus 1 minus lambda m. Now using this relation here, I can now write lambda m minus 1 as m divided by m minus 1 lambda m minus lambda m. From here you can easily see that I will get lambda m into 1 divided by m minus 1. M is the order, so we know this is already a very huge number, so I can approximately write it as lambda m divided by m, and we are given lambda m as 1 micrometer, that is 10 to the power minus 6 meter, and we already calculated the order m, that is 2 into 10 to the power 4, that we have calculated in the first part of the problem. And if we do this, we will get 0.5 into 10 to the power minus 10 meter, which I can write as 0.05 nanometer. So this is the required answer. Now let us work out this problem. It has two parts. You are asked to find the radiation pressure force exerted by a steady stream of photons with power P on a perfectly reflecting mirror. Let us do it first. As discussed in lecture 22, we know that the momentum imparted by a photon of wavelength lambda on a perfectly reflecting mirror is the change in momentum delta p of the photon, and which is given by h by lambda minus h by lambda. So this is equal to 2h by lambda. So that is the change in momentum. The radiation pressure force imparted by a steady stream of photons, suppose the stream has n number of photons, then the force would be equal to n into rate of change of momentum by per photon. So this is the total force. Now we have n delta p, we already know, that is 2h by lambda into delta t, this I can write as n into, let me write 2 here, 2n into sc by lambda, and because I have multiplied c up all up, so I will have to put here also c delta t. This guy hc by lambda is the energy of a single photon, so the total energy would be n into sc by lambda for the whole bunch of photons. So if I write delta E is equal to n into sc by lambda, then I can write force as 2 into delta E divided by c into delta t. Now energy per unit time is the power, so therefore I will have 2 into p divided by c. So this is the required answer. Okay, now let us do the second part. Work out the ratio of the displacement of a mirror on which photons are incident with respect to its 0 point fluctuation in position. Let us do it. Say due to the photon, the mirror having mass m and resonance frequency or natural frequency omega m is getting displaced by an amount delta x when a photon is getting incident on it. The kinetic energy gained by the mirror due to the momentum imparted by the photon gets converted to potential energy of the mirror. So as per the conservation of energy principle, so we will have half m omega m square delta x square, that is the potential energy of the mirror, and the kinetic energy would be delta p square by 2m, where delta p, we know that this is equal to 2h by lambda. From this equation we can find out what is delta x. Delta x would be equal to delta p divided by m omega m, which I can now write, putting the value of delta p, I can write it as 2h divided by lambda m omega m. Also we know that the 0 point fluctuation is given by h cross divided by twice m omega m, where h cross is the reduced Planck constant, it is h by 2 pi, and from this expression I have square of this 0 point fluctuation term would be equal to h cross by twice m omega m, or I can write it as h divided by 4 pi m omega m. Alright, and from here let me work out this particular expression. So I have h divided by m omega m, that would be equal to 4 pi x square 0 point fluctuation. Now we have delta x is equal to 2 by lambda into h divided by m into omega m. So clearly we can now write it as 2 by lambda into 4 pi x square 0 point fluctuation, and from here I can write it as delta x divided by x 0 point fluctuation is equal to 8 pi by lambda into x 0 point fluctuation. So this is the required answer to the problem.